Angkor Wat was not born to overwhelm, nor was it built to become the tourist emblem of a nation centuries later. When construction began in the early 12th century, the monument was the answer to a profoundly practical question the ancient Khmer were forced to confront. How could a society living in a highly volatile tropical environment maintain order, power, and long-term stability? From the perspective of scientific exploration, Angkor Wat is not the beginning of the story, but the point where hundreds of years of environmental observation, technical experimentation, and social organization converged. It exists not because the Khmer sought to build higher or larger, but because they needed a center durable enough to anchor the entire economic, political, and spiritual system of their empire. The land on which Angkor Wat stands is a natural paradox. The plains near Tonle Sap Lake provide abundant water and fertile silt that support intensive agriculture, yet at the same time they form an environment that is extraordinarily difficult to control. During the rainy season, vast areas can turn into inland seas. During prolonged dry seasons, the ground cracks and water becomes scarce. In such conditions, the Khmer understood that strength did not lie in resisting nature, but in regulating its rhythms. From the outset, Angkor Wat was embedded within a vast hydraulic network of reservoirs, canals, and moats, structures intended not merely for daily use or ritual symbolism, but to maintain the physical stability of the land beneath the monument itself. The temple cannot be separated from its environmental context. It is part of an artificial ecosystem created by humans to ensure survival.
The construction of Angkor Wat most clearly reveals the level of empirical scientific thinking achieved by the ancient Khmer. This was not a construction project in the modern sense, with a clearly defined start and finish, but a sequence of stages extending over many decades, possibly across generations. The greatest challenge was not raising stone towers, but ensuring that millions of tons of stone could remain stable on soft alluvial soil that changed with the seasons. The Khmer solution was not to harden the ground with rigid materials, but to create a dynamic equilibrium. The massive moat surrounding Angkor Wat was excavated from the earliest stages, functioning as a regulator of soil moisture and pressure, slowing seasonal expansion and contraction while distributing the load of the structure. Beneath terraces and courtyards, layers of compacted sand and laterite were arranged in tiers, forming a semi-elastic foundation capable of absorbing small environmental shifts without cracking the superstructure. This was a remarkably sophisticated geotechnical approach, achieved not through equations, but through generations of lived experience with land and water. Construction did not proceed at a constant pace, but was adjusted to seasonal cycles and environmental feedback. After each monsoon, builders could observe how the ground, terraces, and drainage systems responded before adding new layers above. Angkor Wat thus rose gradually, layer by layer, with each new stage relying on the proven stability of the previous one. This approach slowed construction but ensured long-term durability. The Khmer accepted slowness as the price of permanence, choosing endurance across generations over rapid completion within a single reign. Once the foundations were secured, the next challenge was materials and transport. Angkor Wat was built primarily of sandstone quarried from the Kulen Mountains more than 30 kilometers away. In a society without metal wheels, engines, or developed road networks, moving millions of stone blocks weighing tons posed a logistical challenge even by modern standards. The Khmer solved this by turning water into infrastructure. Artificial canals linked the quarries to the Angkor plain, allowing stone to be transported by rafts and exploiting buoyancy to minimize energy expenditure. This process was likely synchronized with the climate cycle. The rainy season favored water transport, while the dry season focused on shaping, assembly, and carving.
At the construction site, Angkor Wat functioned like a pre-industrial assembly line. The site was divided into functional zones: receiving stone, shaping and finishing blocks, structural assembly, and sculptural carving. Each group of workers specialized in a particular task, all operating under a unified system of proportions and modular design established in advance. Many blocks were cut near their final dimensions at the quarry, reducing work on site and minimizing installation errors. Once delivered, stones were polished at their contact surfaces and fitted together without mortar. Stability came from the sheer weight of the blocks themselves, while wooden or metal dowels were used only at critical points. Over time, the pressure of upper layers compressed the joints further, making the structure more stable rather than weaker. The celebrated bas-reliefs of Angkor Wat were not merely decorative art, but an integral part of the building process. Evidence suggests that much of the carving was done after the blocks were set in their final positions. This allowed artisans to work directly on the completed structure, reduced transport damage, and made it possible to adapt iconography to changing political or religious contexts. As a result, Angkor Wat is not the product of a single historical moment, but of prolonged accumulation and refinement. Alongside stone assembly and carving, the Khmer placed great emphasis on internal drainage. In a tropical climate, rainwater is among the most destructive forces acting on stone architecture if left uncontrolled. Hidden channels were integrated into roofs, terraces, and galleries, guiding rainwater along carefully calculated paths and discharging it into surrounding moats and canals. This system protected carved surfaces from erosion and demonstrates that Khmer builders always thought in terms of maintenance and long-term operation, not merely initial completion. Angkor Wat, therefore, is not simply a monument of stone, but the product of a fully synchronized social system. Maintaining a construction site for decades required an economy capable of producing large and reliable surpluses. Rice agriculture, supported by extensive hydraulic infrastructure, fed tens of thousands of workers who were not directly involved in food production. Alongside builders and sculptors were labor groups responsible for canal excavation, transport, tool production, granary management, and workforce coordination. From a systems science perspective, Angkor Wat is merely the visible apex of a vast social machine in which every component depended on the others to maintain equilibrium. Beyond its technical functions, Angkor Wat was conceived as a stone model of the cosmos. Its layout reflects Hindu cosmology, with Mount Meru at the center and surrounding layers representing different planes of existence. The temple's east-west axis was aligned with extraordinary precision to the sun's apparent movement. At specific times of the year, particularly near equinoxes, the rising sun aligns perfectly with the central axis, producing powerful symbolic light effects. These phenomena were not accidental. They resulted from long-term astronomical observation integrated directly into architecture, revealing a form of empirical science inseparable from belief.
The decline of Angkor did not occur through a single catastrophic event, but through a prolonged process in which the system became too complex to sustain under changing climatic conditions.
Extended droughts, alternating with extreme rainfall, overwhelmed a hydraulic network optimized for earlier stability. As maintenance demands grew and central authority weakened, failures cascaded through the system. Angkor Wat endured due to its enduring religious significance, but its role as the political center faded, and tropical forest gradually reclaimed much of the surrounding urban landscape. The historical significance of Angkor Wat thus lies not in lost grandeur, but in the lessons it preserves. It demonstrates humanity's capacity to build extraordinarily complex technical and social systems under severe constraints, while simultaneously warning of the limits of adaptation when environmental change exceeds original assumptions. Angkor Wat helps modern science better understand the past while posing a question for the present and future. Are today's cities and infrastructures sufficiently flexible to confront long-term climatic volatility? Or are we repeating, on a far larger scale, the challenges once faced by the Khmer?